Hello everyone, welcome to another session of Code with a Friend. So today we will continue our learning of Rust. This is the third session of Rust, and in our last two sessions we covered like how to create a basic Rust project, how to write like hello world program in Rust, write a small guessing game program in Rust. We understood like the data types, what are there, and also some of the basic control flow structures. Um, so yeah, let's get started. So today we'll be covering understanding ownership, which is I think it's a unique feature for Rust and it has implications for the rest of the language. So let's see how it actually works. So we'll talk about the ownership as well as the related features, borrowing, slices, and how Rust lays out data in memory. So what is ownership? Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use the computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach, which is memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. So everything like every these mapping sort of shifts to compile time checking. Because ownership is a new concept for many programmers, it does take some time to get used to, of course. The good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you will find it to naturally develop code that is safe and efficient. Keep at it. Yeah, I guess like the from my perspective, mostly people are familiar with the garbage collected method. If, for example, from my perspective, I'm more familiar with the Java side of the world. But I also know like how C and C++ manages memory, which is explicitly the programmer's responsibility to allocate and free memory and how we want to do that. Java does sort of garbage collection. Um, so if you have unreferenced location, probably it will be garbage collected, but it depends. And it's also an expensive operation. It consumes a lot of processing resources. So this ownership concept is different. So let's see how it works. Many programming languages don't require you to think about the stack and the heap very often, which is right. But in a systems programming language like Rust, whether a value is on the stack or a heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and heap. So I think in our last session, we were trying to refresh our understanding of stack and heap. So just to recap, stack memory is anything where the local variables are stored. For example, if we have a main function and then another function within that. So every time we are calling a function in that context, all the local variables will be stored. And whenever we are returning, like the control flow is going out of the function's context, all the local variables within that stack will be eliminated. So you will automatically free those memory. And then heap is something where you can allocate dedicated memory and across stack, you can still continue to access them. You just need to have like some kind of pointer to that location. So that's it in the understanding of stack and heap. So both the stack and heap are parts of memory available to your code at runtime, and they are structured in different ways. The stack stores values uh, in the order it gets them and removes in the opposite order. That's I think typical stack. Um, Last in first out philosophy. This is referred to as last in first out. Think of the stack of plates. Yeah, I think we all know what a stack is. Popping off, yeah. The heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of the location. The process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values on the stack is not considered allocating. Because the pointer to the heap is a known fixed size, you can store the pointer on the stack, but when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you have been seated to find you. Pushed to the stack is faster than allocating on the heap because the allocator never has to search for a place to store the new data. The location is always at the top of the stack. Makes sense? Comparatively, allocating space on the heap requires some work, more work, because the allocator must find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A and an order from table B, then an order from A again, and then from B again would be a much slower process. By the same token, a processor can do its job better if it works on data that's close to other data as it's on the stack rather than farther away as it is can be on the heap. When your code calls a function, the values passed into the function, including potentially pointers to the data on heap and the function's local variables, get pushed out to the stack. When the function is over, the values get popped off the stack. Makes sense. Once you understand ownership, you won't need to think about the stack and the heap very often. You know the main purpose of the ownership. Okay. So ownership rules. So first, let's take a look at the ownership rules. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Um, Background is. Let's make Cool. Variable scope. Okay, so now I think we are discussing scoping. We are past basic Rust syntax. We won't include the function main. Right. So at the first example of ownership, we'll look at the scope of some of the variables. Scope is the range within a program for which an item is valid. Take the following variables. So I think if we have S, so ownership rules are each value in Rust has an owner. There can be one owner at a time. When the owner goes out of scope, the value will be dropped. Hmm. That is interesting. Value of the string is hardcoded text of our program. The variable is valid from the point at which it's declared until the end of the current scope. 4.1 shows a program with comments annotating where the variable s should be valid. S is not valid here. It's not yet declared. S is valid from this point forward. The scope is not. And there are two important points. When S comes into scope, it is valid. It remains valid until it goes out of scope. Hmm. Okay. In case of string literal, we know the contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient. The properties only come from the immutability. Unfortunately, we can't put a blob of memory into binary for each piece of text whose size is unknown at compile time, and the size might be changing. With string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. This means memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with our string. That first part is done by us when we call string from. Its implementation requests the memory it needs. This is pretty much universal in programming languages. Okay, so I think the example that they're choosing is, yeah, a complex data type, which is the string type. The previous or known size can be stored on stack and popped off the stack when the scope is over, can be quickly and trivially copied to make a new independent instance. I think that makes sense. We want to look at the data that's stored on the heap and explore how Rust knows when to clean up that data, and the string type is a great example. We'll concentrate on the parts of string that relate to ownership. We have already seen string literals, and where a string value is hard-coded into our program, string literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they're immutable, another is that not every string value can be known whether we write our code. For example, what if we want to take user input and store it? Rust has a second string type. This type manages data allocated on the heap as much as able to store an amount of text that is unknown to us at the compile time. You can create a string from a string literal using the from function. Cool. Okay, so memory and allocation. There is a natural point at which we can return the memory of our string from allocator when S goes out of scope. When a variable goes out of scope, Rust calls a special function for us. This function is called drop, and it's where the author of string can put the code to return memory. Rust calls drop automatically at the closing curly bracket. So it's like an automatic destructor for the allocated operate. And in C++, this pattern of deallocating resources at the end of an item's lifetime is called resource acquisition is initialization. The drop function in Rust will be familiar if you have used RAII patterns. Got it. Probably we can read more about this. Um, Object lifetime and resource management, resource acquisition is initialization. Particular language behavior, holding resource is a class invariant and it's tied to the object lifetime. Resource allocation or acquisition is done during object creation by the constructor, while resource deallocation is done during object destruction by the destructor. In other words, it must succeed for initialization to succeed. Thus, the resource is guaranteed to be held between when initialization finishes and the finalization starts. RAII is associated most prominently with C++, where it originated. It also Ada, Vala, and Rust. The technique was developed for exception-safe resource management in C++ 8489 by Strauss-Schrupp and Draconic. The term itself is coined by Strauss-Schrupp. RAII is generally pronounced as Ishalism, sometimes pronounced as RAII. Yeah, so let's see a C++ example. Even, I mean, I'm not a C++ expert, so I don't know how I might be able to read that, but okay, essentially it just says writing to a file. So I have a message, a reference to a message string. Mutex is to protect access to file, which is shared across threads. Now the log guard is to mutex, log mutex before accessing the file. Now try to open the file. If file is not open, then unable to open the file, then write the content. File will be closed first when leaving the scope regardless of exception. Mutex will be unlocked second from lock destructor when leaving the scope regardless of exception. So we don't need to explicitly do that. So this is exception set because C++ guarantees that all stack objects to be destroyed at the end of the enclosing scope, known as stack unwinding. The destructors of both log and file object. Okay, so which means C++ already did that. I didn't know like this before. So, so this is similar to what Rust is doing here. So resource acquisition is initialization. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of the code can be unexpected in more complicated situations when we want to have multiple variables use the data we have allocated on the heap. Mm, yeah, something like that. For example, like x is 5, then y is x. We can probably guess what is this is doing, right? So essentially, like now we have two variables which is pointing to the same memory location. Because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now, if we look at the string version, this looks very similar. So we might assume that the way this works would be same. Second would make a copy of the value in S1, but this isn't quite it happens. Okay, so in first case, we're actually creating copy. Okay, so it becomes easier to manage their individual scopes. Like we don't have to keep like a um, counter of how many of them are doing that. But in this case, we have to have a counter, right? So under string is made up of three parts shown on the left. Pointer to the memory that holds the contents of the string, a length and capacity. The group of data is stored on the stack on the right hand side, memory on top of the heap. That's what's the contents. Makes sense. And the length is how much memory in bytes, and the capacity is total amount of memory in bytes has received from the allocator. The difference in length and capacity matters, but not in this context. When we assign S1 and S2, then now we have the same thing. So essentially these two are replicated, memory locations are same, meaning that we copy the pointer, the length and capacity in the stack, we do not copy the data. Cool. The representation does not look like figure 4.3. I think in these particular cases, if we have like a two-way pointer, it's easier to manage. It does not look like figure 4.3, which is what memory would look like if Rust instead copied the heap data as well. That would be very expensive at runtime performance. Yeah, exactly. I mean, if we have like a very large allocated string and we have to replicate that, that's not efficient. Calls drop function and cleans up the heap memory, but figure 4.2 shows that, yeah. So this is a problem because now if one guy goes out of scope, for example, if S1 goes out of scope, S2 can still access the data. They will both try to free the same memory. This is known as double free error. Yeah, that's one of the memory safety bugs. Freeing memory twice can lead to memory corruption. I think I was thinking from the other way around. Like, should you free memory if one of them is already using it? After this, Rust considers S1 as no longer valid. Interesting. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Ah, this is interesting. Check out what happens when you try to use S1 after S2 is created. You'll get. Ah, this is interesting. I never expected this to happen. But it actually makes things quite simplified in terms of the compiler. If you design a different kind of programming patterns. If I have already have a variable pointing to a memory in heap, and I just create another variable to point to the first variable, then the previous variable gets becomes invalid. So you're just transferring ownership. You cannot have like co-ownership, shallow copy, deep copy, then yeah, I think this is essentially a shallow copy. Pointer linked without copying the data. This, yeah. Rust also invalidates the first variable instead of being called a shallow copy, and it's known as a move. Yeah, it's not a shallow copy, it's a move. S1 was moved to S2, so that's actually happened. This is interesting, as I mean, I never expected this could happen. I mean, a language could do that. This is fascinating. That's also a problem with only S2 valid when it goes out of scope. It alone will free the memory and we are done. That makes, I think, it's so at any point in time you can ensure like there is only one ownership. So if whoever is the owner goes out of scope, um, I mean just free the content whichever the owner is holding. Makes life much simpler. In addition, there is a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. That makes sense. Yeah, I think there is no deep copy. There is no shallow copy as well. It's a move that happens. So if you are doing that kind of assignment, just be aware that it will be just transferring ownership. We do want to deeply copy the heap data of the string, not just the stack data. We can use a common method called clone. So we'll discuss this in there. I think that's fairly straightforward. I think in this case we will have the code working. When we see a call to clone, you know that arbitrary code is being executed and the code may be expensive. It's a visual indicator that something different is going on. Yeah, yeah. Makes sense. So you become very explicit when you call cloning. Stack only data. There's another wrinkle we haven't talked about yet. The code using integers, part of which was shown in listing photo works and is valid. So we have x is 5, y xs, x. But this code seems to contradict what we just learned. We don't have a call to clone, but x is still valid and wasn't moved into y. The reason is that types such as integers that have a known size at compile time are stored entirely on the stack. Uh, oh, yeah, yeah, yeah. So this actually works, right? Because this is not heap allocated memory. So it happens like a deep copy. So copies of the actual values are quick to make. That means there's no reason we would want to prevent. So what happens if you have like an array structure? Now I think I'm more interested. Should I just open the code here? Cargo new ownership. So let's open the main.rs ownership. Let x be 1, 2, 3, 4, 5. Right, and I also want to create a print function which will pass an array. So I don't know how to pass an array data type. And what I'll do is for I in x, println something like this. I want to do. How do I do that? I don't like this. Won't work. So expected. How do I specify a type name here? So I want to pass in an array type in Rust function. Yeah, so we just type semicolon capacity. That's I think that there is um, how do we specify if that a function is actually holding, I mean passing, what should I call it, like pass array as a function? Yeah. Oh, if I don't want mutable, just is this fine? Let's say I don't want to just do this just for simplicity. Just I guess this is fine. No, this is not. So doesn't have a size known at compile time. Or let's say something like this. So now it's all warning. Unused variable, um, unused here. Function print is never used. Ownership generated one warning. Okay, so this print is never used. Let's actually use print. So this actually works. So we have to specify what's the size of it. Um, okay. What if I don't provide this? The trait size is not implemented in i32 function arguments. Okay. So if I just provide the reference, expected ampersand. Okay, so now I think this is fine. So got it. If I and I can pass, let's say, length or something, which is another i32. I can say from here print this. So it's a very C-like structure for I in one dot dot len. Does it work? It's all warning. Unnecessary parentheses around for iterator. We don't need that. Okay. And unused variable I. Okay. Okay, so this works. And I can here say println score x. Will this work? type I32 cannot be indexed by I32? Okay, let's I think first see if this pattern works. Like I just in the printing pattern. So the printing pattern works. The type I32 cannot be indexed by I32. Okay. The trait slice indexed I32 is not implemented for I32. Yeah. 277. I guess it's because I'm passing this reference here. Uh, Rust references denoted by the ampersand sign are of two kinds, immutable and mutable. In order to change a value, okay, if I do not need to change the value, how do I access it? Okay, let's just run it and see. So I think this works. Can I do like this? That also works. Can I do like this? That also works. But this is, I think, fine. And I'm not able to index this, right? So required for array I32 to implement index I32. So I think that understanding is not clear yet. Sending arrays of unknown length to a function. Um, Return. Okay. So, well, it won't matter, right? It won't matter. You need to pass a reference, not the array itself. So similarly, we are passing the array here. Yeah, I said the same thing. X is not given, it's not comparing a compiler infers that it should have the UN. Okay. Not very helpful. Should I be able to do that here? Yeah, let's forget about it. Okay, so that actually works, but this doesn't work. What about the iter function? So will this work here? Underscore x dot iter. Okay. That works. Oh, okay. We don't need this then. We don't need this then. So we can just. So array has an iterator which does iteration for itself. Okay. I guess my entire point was to this. We are able to print, like initialize and print an array. Now I just want to switch or move ownership. Um, what happens to this? This works, right? So essentially means this is doing a deep copy. Is this doing a deep copy because I'm allocating it at compile time? I don't know how to create a dynamic array in Rust, um, but that we can place on types that are stored on the stack as integers are. We'll talk more about traits in chapter 10. If a type implements the copy trait, variables that use it do not move but rather are trivially copied, making them still valid after assignment on the variable. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the values goes out of scope, we add the copy annotation. So what types implement the copy trait? You can check the documentation for the given type to be sure, but as a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation on some form of resource can implement copy. Here are some of the types that implement copy. All the integer types such as U32, the Boolean type bold with values true, false. All the floating point types, F64, character type are tuples if they only contain types that also implement copy. Okay, so there are like some specific rules. I don't know like if I understand ownership fully yet, which is not also expected because I'm reading it first time today, reading about it. The mechanics of passing value to a function are similar to those when assigning value to a variable. Passing variable to a function will move or copy just as assignment does. Huh. Takes ownership. Ss values moves to the function. Hmm. Okay. Come here. X is 4, max copy. Ss value moves into the function. Uh-huh. X comes into scope. X would move into the function, but I32 is a copy, so it's okay to still use X afterward. No, what did it mean by using safe? So what if I, let's run this first. So this is there, right? And now I guess if we do println this, ah, Okay. Value moved here. Oh, so this is actually quite interesting. So if the value is moved here, then the value is sort of gone from that stack. Unless we have a mechanism to copy it back. Um, can I do like this kind of thing? What happens then? Mismatched types. Okay. If I say that I return string, cannot assign twice to immutable variable. Let me just create another variable. That works, right? Okay, so now I think I'm slowly trying to understand. Like, even though the language manages a lot of the memory, it pushes the overhead to the programmer. So basically, I have to now, which I think it's still fine. You develop the habit of managing the memory overall. The takes ownership function actually moves ownership from the main function to the takes ownership. And then at the end, after doing operation, I just dump the same string and get the control back in the previous function. Now the previous function can continue to do operations with that. So this is essentially what's happening here, which makes sense. It's actually quite clear to do it in that manner. Um, so the last part, I think it's called return values in scope. So this is, I think, something similar that I was trying here. Um, Obviously, like if the ownership is moved to the function, then you can always move back the ownership, and that is through the return values you can do. I think there might be some complicated ways of passing references and then assigning it to back, but at least the straightforward ways is just you take and move back ownership. So whatever you take, you just move back S3, something similar. Um, right. For example, calculate length S1. So what? Every function has like a cost, right? Because what you'll essentially do, you're moving ownership of whatever you are transferring to that function. So you have to move back uh, the stuff, calculate length, and then we do like, oh, okay. I think, yeah, this is, I think, powerful. So that's, I think, what I was talking about. If you can return multiple values, this is super powerful. I mean, returning multiple values, then you don't need like passing by reference, passing by, that's, I think, all mess. Super like. Okay, now I think at what stage are we? Let's see if we can cover at least the understanding ownership part. So the issue with tuple code in listing 4.5 um, is that we have to return the string to the calling function, so we can still use the string and the call to calculate length. Because the string was moved into calculate length, instead we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at that address. The data is owned by some other variable, and like a pointer, a reference is guaranteed to point to a valid value of a particular type. Calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. Oh, so okay, so there is this reference concept. Yeah, because the string was moved into, instead we can provide a reference like a pointer that address we can follow the access to the data. Data is owned by some. Then I think it breaks the contract, right? Unlike a pointer, reference is guaranteed to point to the valid value for the life of that reference. Here is how you define and use a calculate length function. So we pass a reference to it, and then let's go back and actually we can do everything in this ownership file itself. Let's call this test one. And if we don't want to call this, I'll just have test2. String from hello, and we go let len is calculate length percent s1, calculate length s address of string uses s.len. And if we do println here, the length of s1 is len. Is there a way to assume, like, just say, okay, I'm fine to have it, like, oh, we can't do that. Yeah, I think it should alarm us at least with warning, but at least this part is fine. So calculate length, it's returning a size, run. The length of hello is 5. Okay, so all the tuple code in the variable declaration and the function return value is gone. We pass ampersand s1 into calculate length, and its definition we take ampersand string rather than just a string. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. Okay, so ampersand is pointing at s1. The opposite of reference by using ampersand is dereferencing, which is accomplished with the dereference operator. We'll see some uses of the dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. Ampersand s1 syntax lets us create a reference that refers to the value of s1 but does not own it. Because it does not own it, and the value it points to will not be dropped when the reference stops being used. Likewise, the signature is okay. The scope in which variable s is valid is the same as any function parameter scope, but the value pointed to by the reference is not dropped when s stops being used because s doesn't have ownership. Okay. So there is like another concept and references. And when functions have references as parameters instead of actual values, we won't need to return the values because we never had ownership. We call the action of creating a reference is borrowing. So that's the same as borrowing. I thought like borrowing might be another concept that would have been complicated. If a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. So what happens if we try to modify something when borrowing? Yeah. So we can't modify, right? It's a read-only thing. Yep. Just as variables are immutable, so are references. We are not allowed to modify something unless if we have a reference. Um, can just do mutable string argument. Okay, yeah, I think we have to pass like a mutable string. No, actually, we don't, right? I mean, this should be a different function. This should be like, yeah, change or something. Main thing will be in our main function. So let, yeah, this will also have to be mutable, of course. Anyway, like wherever we need to do it, then we do a change ampersand mutable. Yes. The problem with flexibility is yeah, so I was just saying the problem with flexibility is it depends on the design choice. Um, if I want to just make it work, I can make it work by just doing random stuff. Um, but yeah, I don't know. Yeah. Okay. Okay. So that is out of there. The problem with flexibility, I think, is yeah, the same point that I was mentioning. Like if I just want to make some feature work, let's say I'm developing some feature in Rust and I want these kind of things to work. I can make it work in by exploiting all the options that the language provides. Either the language itself be very opinionated about how things should be done, how we should create access patterns and stuff like that. So if Rust believed in the ownership concept, um, you I mean, let's say if Rust believed only in the ownership concept and not allowing any function to mutate data or not allowing any concept of mutability at all. So you have everything immutable. Whenever you are creating something, you have to do it at a cost. Um, that kind of thing, I think it's harder for a language design perspective to take that into consideration. But what happens in real life software development is those things come into play. But because you have to be opinionated to some extent within your scope, within your feature, or within your product, like this is the way that we want to do this helps us to scale. That's, I think, what I have seen in my prior experience, and it might also, opinions can vary, but that's also one thing that I noticed a lot. Anyway, so coming back to our code again, this should not happen. What is we are trying to do here? Mutable references. So R1 we say mutable reference to S, R2 is mutable reference to S. Okay, so error says that the code is invalid because we cannot borrow S as mutable more than once at a time. The first mutable borrow is in R1 and must last until it's used in the println bang. But between the creation of that mutable reference and its usage, we need to create another, which is not allowed. The restriction preventing multiple mutable references to the same data at the same time allows for mutation to be in a very controlled fashion. It's something that new Rustaceans struggle with because most languages let you mutate whenever you like. Yeah, of course. The benefit of having this restriction is that Rust can prevent data access at compile time. A data race is similar to a race condition that happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write the data. There is no mechanism being synchronized to access the data. Yeah, so I think this is something that I was talking about. Like if we want to, if Rust, for example, allowed that multiple mutations, which a lot of languages allow, then it becomes like the focus of feature developers or senior engineers to design that kind of um, what should I say, like a soft restriction on top of the bare language. In a lot of the sense, they are like there are like DSLs, like domain specific languages, and something like that. So you define your restrictions of your domain on top of like the base language, and then you scale on top of that, so that not everyone needs to be aware of every single issue that happens downstream. I think the overall goal. I believe like abstraction has its own value, but uh, yeah, I'm sort of diverting a little bit. But anyway, so data races, but I think this is a good behavior. So in that way, Rust explicitly says, okay, I have a mutable variable and I have a mutable reference, but you cannot create like another mutable reference. And then I think it's very hard to create synchronization. So data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Absolutely. Rust prevents this problem by refusing to compile code with data races. This is beautiful. I mean, I gave like 100 points to Rust for that. Like you prevent those kind of scenarios to happen in the first place. As always, we can use curly brackets to create new scope, allowing for multiple mutable references, just not simultaneous ones. So we have let mutable s string from hello. Um, okay. So this goes out of scope, which means like that is dead, like that's technically like not together. Um, Rust enforces a similar rule for combining mutable and immutable references. Like if you have mutable, immutable are fine, mutable. Oh, okay. That is interesting. So you cannot also have immutable reference, mutable references together. That's, I think, interesting pattern. We also cannot have a mutable reference while we have an immutable reference. Users of an immutable reference don't expect the value to suddenly change. Multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. A reference's scope starts from where it is introduced and continues through the last time the reference is used. For example, this is this. Yeah, 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 yeah. No problem, no problem. Println this. Okay. The scope of the immutable references R1 and R2 end after println bang when their last use, which is before the mutable reference R3 is created. These scopes don't overlap. So this code is allowed. Even though borrowing errors must be frustrating at times, remember that it's Rust compiler pointing out potential bug early and showing you exactly what the problem is, and you don't have to track down why your data isn't what you thought it was. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have references to some data, the compiler will ensure that the data will not go out of scope before the reference to that data goes. Um, the compiler will, data will never go. Okay, yeah, yeah, of course. So let's try to create a dangling reference and see how Rust prevents that. So reference to nothing, it's dangle address of string. Yeah, yeah, of course. Yeah. The error message refuses the feature that we haven't covered yet, which is lifetimes. Okay, that's I think interesting. Lifetime in chapter 10, if you disregard the parts. Okay, yeah, yeah, yeah. So dangle returns a reference to a string which is dropped out of scope because it is created inside dangle. It's finished, S will be deallocated, yeah. So no dangle, I think it's a copy thing, is to return the string directly. So this works. Ownership is moved out, nothing is deallocated. Oh, this is amazing. So you can allocate inside and just copy S. That is superb. So potentially we can create stuff within another function, move ownership back, rather than moving the pointer back, which is, I think, or the reference back. Awesome. So I think this is good enough for today's session. So we have covered deal references and borrowing. So we'll start with the slice type in the next session. There are a few more things using structs to structure related data, enums and pattern matching, managing growing projects with packages, crates, and modules, which I'm, to be honest, like I'm more interested in the language initially. Packages probably, I don't know if we can go into that later. Common collections, even I think that is something I'm interested. Error handling, generates types, traits, lifetimes, automated tests. That's I think interesting. An IO project, command line program. Yeah, that'll be quite interesting. Functional language features, iterators, closures, cargo and crate, smart pointers, fearless concurrency, object-oriented programming features, patterns and matching, advanced features, unsafe Rust, and building a multi-threaded web server. That's interesting. Appendix. Cool. So that's I think for today. There is like a lot of things that we can cover. The way we are progressing, I think it'll take at least 25 sessions, 25 to 30, depending on like the complexity of the later sessions. And we are just in the beginning. So this is the third session. So let's see. I'm excited. Yeah. Cool. See you in the next session. Thanks for joining. Bye bye.